Here we are at the, again, Simon's problem and Simon's algorithm. So I haven't had so far an aha moment yet, but I wanna try to go to attack the thing again. I guess what I'm trying to do is I'm trying to actually figure out a way to implement the black box so that I can kind of reason about the algorithm. Because from a mathematical standpoint, it's a bit confusing for me. This is the step that's a bit confusing. So up until here, and then I kind of understand there's some other version. If you check out the other videos, the previous video they uploaded, and there's of course some other articles where they talk about some measurements in the middle and stuff like that. So, but basically, what this all boils down to is that. So if that's a circuit, so if we've got the first register here, then there's like a Hadamard on the entire register, and then there's the second register here. Remove that. And then we've got the box, and then we've got another Hadamard here, and then we've got the measurements, correct? That's kind of more or less what we have in here. Yeah, and those are initialized both at 0, according to that picture. So as a matter of fact, here we know if we can understand that in here, this is sort of the result of the oracle. That basically we've got a superposition of the input and the output of the function. So basically, this means that there has to be sort of a Hadamard in here on the output register, because the idea is you've got a superposition where the first qubits are sort of, it's a superposition of the input, and then they're kind of mapped to the superposition of the output. So you essentially have actually these as a superposition with equal probability. Oh, come on, this just need to follow me. With equal probability. And so basically, what's happening here is that the next step is you apply another Hadamard transformation into your first register. That's what. Let me see if I can just remove this, because it's following me around and it bothers me. So we apply Hadamard on the second register, on the first register, sorry, and this is where. So this is where sort of the black box is happening, right? Because then we see that this is transformed into a superposition in and of itself of some input elements y, which are also strings, binary strings, and then there's a phase that depends on x times y, being x times y, being these dot products in here. Okay. Which essentially they rewrite it like these. but it's kind of weird. Because in order to be able to do that, it kind of means y is so that it's not in superposition, is it? Because that's it's really weird. I'm missing sort of a coefficient in here, or I just don't understand it. But that indicates there's definitely an effect. But does this happen after applying the Hadamard? So if this doesn't go back to a to x, it essentially means that something has happened. So there's sort of an interaction in between those two qubits in the box, which of course it's kind of obvious because you've got to establish the relationship between the inputs and the outputs when you build a function. But and I'm kind of assuming, I think I'm right, that goes along the same lines like the Deutsch algorithm and the Bernstein algorithm. So probably using control nodes or something like that. Which then in turn have a phase kickback effect, and that's what changes the signs. But then after having performed all previous described operations at the end of the circuit, a measurement is performed. There are now two possible cases we need to consider. So let's first analyze the special case of x times y equals 0, like the zero string. Now the probability that measurement results in each string y is probability of each string y. One way to see that the previous equation is true is to note that because the two vectors only differ in the ordering of the entries. Uniformly distributed in the second case. Let's now analyze the case equals S. Now that in this case f is just a 2-to-1 function. So the probability of y can be written as this. I don't really get it. Don't really get where this is coming from. Then this classical post-processing will run the circuit. You have the case in the special case where measure results in each string with probability. In the case where x times y equals s, probability to obtain each string is given by 0 if y times s is odd, and okay, if y times s is even. Because in both cases the measurement results in some string y that satisfies that s times y equals 0. This is how, okay, so wait a second. So this is how then, okay, so this is probably what I should try to understand. So it's telling, okay, so it's basically telling us the measurement is going to give us a string y that multiplied by s equals 0. This is enough information to determine S. The answer is yes, provided that the process above is repeated several times and a small probability of failure is accepted, especially if the above processes run n minus 1 times, we get n minus 1 strings, such that this is a system. This is a system if n minus 1 of n minus 1 linear equations in n unknowns, the bits of S. And the goal is to solve it to obtain S. Okay, because S, okay. Okay, that's XOR actually. That's the bitwise XOR. Okay, so this is what this is saying is, okay. See, I'm getting there. It's a bit, you can't hear my mind, but I think I'm getting there. I think the thing is, these Y's are going to be sort of masks that basically tell you where has some of those control nodes I was talking about been applied. I'll try to explain that in a second. But then that mask will only particularly give us like potentially some information about S, because remember that so if we've got like a binary string S, I'll just make up like 0, 1, 0, right? But we didn't know that's this, right? So we kind of got like, or better, like XXX, right? And then we've got a sort of a Y that is like, let's say this is 0, 1. It's going to be easier for my example. A Y that's like these, right? No, something's not right. So if we know that this X or this, so this X or this is the 0 string, is 0, right? Sorry, I'm awful at maths, as you can see probably. So they cannot all be X because we obviously don't know them. So it's X, Y, Z, right? And then we've got like 0, 1, 0. So we basically know that X times 0 plus Y times 1 plus Z times 0 equals 0. That's what that's what this is saying. This whole reasoning in here. And then, yeah. So if then you get another Y, that is, let's say, 0, 0, 1. No, not exactly, but I think it's going somewhere in this direction, because, so what I have in mind is the following. So what if the circuit is as follows, right? Inside the box. So let's try to do it for the table in here. So let's try to paint the box, right? So let's just the box. So here you've got like a register that's, so we're using three qubits. So we're going to need 6 qubits. So you're going to have these 3 qubits, and then we're going to use blue for the output qubits. And basically, let's imagine we've got a superposition here, right, of plus, 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 and then another one here, plus, plus, plus as well, right? So this is, and here starts the box. Okay, you can argue whether the plus, plus, plus happens inside the box or not, but let's assume we have it already. So what's going to happen, one way to implement these, right, is by using basically like 3 TOEFLs per each entry. Yeah. So, for example, you would say, and this is probably not the optimal way to implement that, okay? But it's just so I can. So you would kind of get, for example, for the 0, 0, 0, right? You've got like a TOEFL that's like empty, 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 right? Because it's 0 is what we want, and then it has a control node in here. And then there's a control node in here as well, right? So that basically establishes this relationship. Is this correct? I'm not sure. I'm not sure. But we can, I can try to build it in Quirk and see if that's, maybe it's even better than this. So I'm going to keep that on a separate tab so I can take a look at the table, but you're not going to see the table. So Quirk. So we're going to have basically, how can I easily? So we're going to have 6 qubits. That's the first register, and that's the second register. Okay. And then what we're gonna do is basically say, okay, so I'm taking a look at the table. So for 0, 0, 0, the output is 1, 0, 1. So I'm gonna say for these output we want the next here and the next here. Okay. Why doesn't this have any effect? Because if this would be a 1, then we're getting, so let me take a look at the, I want to take a look at is it the amplitudes? So that's definitely not the way to build it. How can I build that? How can I build exactly that particular? That's actually harder than I thought. Unless I do this. Makes no sense, absolutely. What if I get, again, I'm not using the shortcuts because I'm using the trackpad. So Okay, maybe this actually works. Because we're acting on the superposition, and then this is not in superposition. I mean, let me check. Now I would do for 0, 0, 1, I want 0, 1, 0. So for 0, 0, sorry, this goes way here. 0, 0, 1, I want 0, 1, 0. So I want just these. Okay. Yeah, so I'm kind of building the superposition step by step. I'm taking, look that I'm actually stealing probability from the 0, 0, 0. It's interesting. Okay, next one is for the input 0, 1, 0, we want 0, 0, 0. So we're not going to do anything here. For the input 0, 1, 1, we want 1, 1, 0. 0, 1, 1. I mean, for the previous case, I have to do something, actually. What did I say? 0, 1, 1. So, and for 0, 1, 1, we want 1, 1, 0. So we want 1, 1, 0. Okay. Now for 1, 0, 0, we want 0, 0, 0. Okay. And now for 1, 0, 1, we want 1, 1, 0. 1, 0, 1, 1, 1, 0. For 1, 0, 1, we want 1, 1, 0. Also, is that correct? For 1, 0, 1, 1, 1, 0. Yeah. For 1, 1, 0, we want 1, 0, 1. For 1, 1, 0, sorry. 1, 1, 0, and I'm almost done. 1, 0, 1. 1, 0, 1. And for 1, 1, 1, we want 0, 1, 0. This is for 1, 1, 1. I forget what I said. 0, 1, 0, 0. 0, 1, 0. Okay. So now we've got like, so if I did this correctly, I'm not so sure though. I mean, let's see. Those things should map. So for example, for the input 1, 0, 1, we want 0, 0, 0. No. Oh, sorry. I think it's the other way around. I think the last 3 here are the bottom 3. So for 1, 1, 1, for example, we want 0, 1, 0. 1, 1, 1, 0, 1, 0. Correct. This is correct. Okay, so let's take a look at, so for 1, 1, 0, we want 1, 0, 1. 1, 1, 0. 1, 1, 0, 0, 1, 1. No. Yeah, but maybe that's fine. Maybe that's actually supposed to be this way. Because basically, if I take a look at the amplitudes in here, you've got an equal superposition, and the amplitudes in here, if I now do Hadamard's, are kind of different, right? But I'm not sure if that's the right thing to build this. I'm not sure if that's the right thing to build a box. So, can I see a chance display? for the whole thing. So we've got these possible strings that would pop up. Zero on one, 0 on 1. 0 on 0 on 1, 1 on 0. Right? Unless that's not the way that we're supposed to be building this. So here we've got four different outcomes. A superposition of 4 different outcomes, right? Are those the 4 possible ones in here? So we've got 0, 0, 0. Yeah. We've got 0, 1, 0. 0, 1, 0. We've got 0, 1, 1. No, and that's not in there. That's not in there. So that's definitely not a way to build this. Okay, so my intuition failed in here. Because I was kind of thinking that, but for phase estimation, for phase kickback to work, this would have to be initialized to 1. Otherwise, it wouldn't make any sense. Because otherwise, there's no phase kickback anywhere. That's what kind of plot. I'm gonna bookmark this just so I can come back later, just in case. Simon, take 2. That's definitely not a way to build it. Because what I want to have here at the end is a superposition of the outcomes of the function. So it's a good exercise to try to figure out how to build that, though. Because then another way to go about it would be that clear all the circuit, and then indeed we would kind of have a superposition for the input register. Then we would have a superposition for the output register. Right? And then basically we just need to eliminate here the answers that we don't want, right? For example, we don't want 0, 0, 1 because it doesn't exist. Or we want to tie somehow the inputs to the outputs. So if I would now actually do the same, what if I would now do the same? So if I would say, let me just maybe go back to not here. I want to go back to the one that I just bookmarked. How can I do that? Let me just go to the bookmarks. These bookmarks. Here you go, and I just have to look for Simon take 2. So okay, so if I would now add Hadamard's in here, well, what would happen really? So take that out, and then let's add also Hadamard's in here. And we would have that like that with the one. So now you have that effect. So I mean, here we've got nothing. Here, it just doesn't make any sense. Just doesn't make any sense. Doesn't make any sense to me. How could I then solve for this? Because I would probably need to use an extra ancilla qubit to basically cancel things out, right? So but that still probably would not kind of help me in linking these things together and actually having that superposition. So, but that's one challenge. So I can address this in the next video. But then let's assume we have that. How come that once we then apply the Hadamard in here, just in here, that so what is it that we're getting that then kind of turns into something that satisfies this the y times s equals 0, because we're measuring everything in here, the input and the output. Again, maybe we're just measuring the first register. I don't know. Kind of it looks like, because we're talking about n all the time as n being the number of qubits, which is kind of the size of the register is kind of 3. So basically, I just hate this. People, I hate this. It's just super confusing. Because basically what they're saying here is what you're measuring is you're measuring y's that are like an n long binary string. So that's got to be probably the top register what you're measuring. Because otherwise you're just gonna get, yeah. Okay, so that's good. That's a good thing. Then times s equals 0. So why? And so I'm thinking that the way this that's why I think that the way this works is that the string you're getting is sort of a partial mask of s. So basically, it's the modulo 2 product. So it's the modulo 2 product. So this is what you're getting is the modulo 2 product, which means this times s is bitwise, the bitwise multiplication, and then XOR. Okay, so it kind of means it's not XOR. Sorry, this this is the modulo 2 edition in this case, I think. Yeah. Modulo 2 dot product. Yeah, but kind of essentially. So why is that true? Because the number you're getting. Yeah, it looks like I probably really have to try to build that superposition to try to fully understand what is this that I'm getting, and why am I getting it. So I got to figure out a way to build that, and I could probably look for examples, but I'm going to try to do it without, and it's probably going to take quite some videos. Let's build a superposition. Any superposition. No, current superposition, scientist build machine. Oh, come on. How about the quantum entangled blockchain that travels? Just go away. An equal superposition. It's not an equal superposition what I want to be on. Of 3 outcomes for a qubit. Okay, so given a 2-qubit system with these 4 possible measurements, only 3 of these measurements are possible. How do you... Okay, yeah, but that's... Suppose that you would like to produce the state. Please note that normalization is necessary. If we want to consider a straightforward way to realize the state, we might want to think in terms of the first qubit being a control, which determines whether the second qubit should be in the state or not. Exactly. I think that's okay. I'm not going to refine that. I think, like I said, I was not far away from. So it's not far away from that. Okay, so that's good intuition. So I'll make another video on then trying to kind of build that. Okay, let's see if I end up with that superposition of those values. Perfect. Because that's going to then help me understand what's the set of y's that we're getting. And my guess is that those y's have to do somehow with this s, but I'm not so sure. But I'm not so sure why. I don't really, because in this case, s is what we're trying to find is that s that if we apply, any x or s, then we have 2 items that have the same element. But how can you do that? How can you do that with that? It must be wrong. Okay, maybe not. Let's see.